This is the way. I am the heavy Mandalorian infantry trooper. And you are here to learn math. Learn math. This is the way. Welcome to 10.1.
Oh, looks like you guys already got started without me. Okay. So we're at section 10.1, properties of logarithms. Another real world example, kind of, sort of. So Pedro works in the city of Phoenix, Arizona, and he needs to figure out when the population increases by increments of 10% from 2010. So I mentioned in a couple of other chapters, you can use these logarithm functions, exponential growth, and or just math in general to predict the future. And that's actually what a lot of places do. They'll hire mathematicians or statisticians or blah, 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 in order to help them predict population growths and things like that. And whether you're that mathematician or not, you need to at least know what they're talking about. So let's learn a little bit more about logarithms. Task 1, properties of logarithms, building understanding. So investigate the properties of logarithms numerically. Okay, so we're going to look at these different values, and we're just going to use our graphing calculator to put those in like decimal form. So I'll show you how to do one or two of them, and then we'll kind of speed through the rest. So let's see here. We got log of 1. Remember, when it's just log of no number, that insinuates log base 10 of 1. So 0. The other one was log base 10 of 10. That, you should know that one. Log base 10 of 10 is 1. And then, what? Log base 10 of 4. We're going to do the natural logs, though. Natural log of e. That one you should probably know. Where's my E button? So natural log of E is 1. Natural log of, what was the next one? E to the 5. Hopefully you should know this one off the top of your head. Is 5. So let's write these in here. So what do we get? We got 0. Oh. So we got log of 1 equals 0. Log of 10 equals 1. Natural log of e equals 1. Natural log of e to the 5th equals 5. Okay, so 0, 1, 10. So log base 10 to the 10 to the 4th is going to be 4. 1 again, 5. Oh, natural log of 1. Do I know that one off the top of my head? I don't know. Let's try that one out. Natural log of 1 is 0. Yeah, see, I think I knew that one off the top of my head. Great. So there is a little bit of a pattern here. So we got set A, log of 1, 10, and 4. And set B, so we've got a couple equals here. Equals. I think that one was equal. So anyway, log of 1 was 0. ln of 1 was 0. So we could say ln of 1. Okay. log of 10 was 1. Natural log of e was 1. So natural log of e, and then log of 4, or 10 to the 4th, I should say, is less than natural log of e to the 5th. So how can we check the results? I mean, shove them into a calculator. We can look at the graphs as well. So use your method to check the results. So we're not going to graph them at this point. But so what general statement seems to be true about the expression log base 10 of b? Log base 10 to the power of b equals b. Okay, there's a little bit more information there. What general statement seems to be true about the expression natural log of e to the a? So the natural log of e is going to cancel each other out. So this is something that we've done before. Again, and the log base 10 of 10 is going to cancel each other out, and that's how we're going to get things out of the exponent. So let's see what that means. Let's look at the graphs of these two things. Okay, so let's consider the graphs of y equals log of 2x and y equals log of 2 plus log of x. Let's look at them. So here they are. Log of 2x, log of 2 plus log of x. Wow, they look pretty similar. They might even be the same here. The graphs appear to be the same. Graph the function that and that together on a graphing calculator. Use the table feature to compare the y values of the two functions. I'll let you do that right now. The functions are still the same. What? All right, so let's actually do it on our graphing calculator. So here we go. They want us to graph log of 2x and log of 2 plus log of x. So here we go. We'll go to our y equals. Clear these guys out. Probably need to turn off my data points. Yeah, totally need to do that. So we're going to turn this to off. That was from last class. All right, so we've got log of 2x. Then we've got log of 2 plus log of x. I don't get it. They still look the exact the same. So we can use our table function. They're the exact same. So which word were they looking for? The functions are exactly the same. Oh, okay, equivalent. They wanted to use a more mathy word. Sure, whatever. But yes, they are exactly the same. So write two other functions that you believe have the same relationship. You can think about that, but we're going to speed through and make a generalized statement. So what general statement seems to be true about the functions of the form y equals log base b of m times n? So if you look through these, this one seems the most similar to what we were doing. Could it possibly be a law or a rule? We are going to graph two other functions. So if we are looking here, we're going to look at the graph of y equals log of x over 2 and y equals the log of x minus 2. We scroll down, x over 2, there's our graph. Interesting, y equals log of x minus log of 2 is the exact same graph. Are we noticing a pattern here yet? The graphs appear to be the same. Graph the functions, use the table feature to compare. The functions are equivalent. Oh, no, I didn't graph it. I'm sorry. I saved you guys all just like 2 minutes. 1 minute if you're watching this at 2 times speed. You can come up with your own, and here's our generalized statement. So we have y equals log of base b of m over n. That appears to be the same as log base b of m minus log base b of n. Could that be a property of logarithms? Property, that's a better word. Property. So properties of logarithms. Holy cow, here they are. Bam. Oh, come on, zoom in. So these are our properties of logarithms. This is something that you should get very familiar with, especially if you're going into a STEM field. You probably want to know this very well. I don't want to say the word memorize, but you might want to memorize this. Just saying. Maybe we'll use it enough to where you'll remember it. So, definition-based properties. This is a thing that you probably kind of figured out from our other work with logarithms. So log base b of 1 is going to be always 0, no matter what your b is. Log base b of b, so when these things match, your answer is just going to be your exponent up there. So we've definitely used that before. And then log base b of b, you have an implied exponent right there. And that implied exponent is 1 when there's nothing there. So some things that we've seen earlier in this lesson are product and our quotient. So these are going to be very handy in the rest of your mathematical careers because everybody's moving on to bigger and better things. So notice log base b mn is equal to log base b of m plus log base b of n. So this corresponds a little bit with the exponential rules. So that's kind of how I remember them. So log base b of m over n is equal to log base b of n minus log base b of n. Super hard to say over and over again, but whatever. So then the power property, this one's a little bit different than our exponents, but log base b of m to the power of n. So again, our base and our m do not match at this point. So what you can actually do is you can bring that n around front. So that is a thing that you can do. And this is going to be, so to change the base of a property of logarithms, that's going to be very helpful. So if you have log base c and you want it to be log base b, you can do that by making log base b of a and log base b of c into a fraction. So that's going to be very handy both in proofs but also just in the world of math as we change log. So we've had some problems in previous problems where we had like log base 1.06. Well, this, we could change that to like log base 10 or log base E, natural log, and then our calculators could handle that a lot easier. Maybe you don't have your fancy calculators that you can change the base on. So this is what you need to know right here. In fact, if you know how to do a screenshot, this might be a good idea to do a screenshot of this chart right here. Because we've gone over a lot of charts, and at some point it's going to be hard for me to have them all on the board at once. So you might want to have that available. But the name of this task was prove. So I already kind of worked through the proof of this, but we're going to work through it together. So here we go. The power property of logarithms property. So we're going to start with, we're going to say let x equal log base b of m. So that means based on our definition of logarithm, we can write it this way, which is kind of what we learned in like 9.1 or something, that you can rewrite your log. So then we can take that and we can substitute that in. So we start with this thing right here, because that's kind of what we're prove the power property logarithm. So that's one of the things that we're trying to work on. We can sub this m in for b of x, because m equals b of x. So that was using substitution. So then we can say the power of a power property of exponents. So we went over that a couple sections ago. Basically, we took a power of a power. We can say that they are the same as multiplied together. Okay, so we've got our same thing here, but you'll notice that we have a log base b of b. So by our definition of logarithm, that's going to equal just xn. And then we can sub our x equals log base b of m back in. And so now we have log base b of m times n. And then we can say that so that is equal to that. So that's just an old school cumulative property of multiplication. We just move that n over to the front. So that is, again, a taste of what a proof kind of sort of looks like. And that proves our power property of logarithms. Try some of these properties out. So we've got a couple of examples here. So it says simplify each expression. Let's zoom in. So we're starting with log base 12 of 9 plus log base 12 of 16. So note that their bases are the same. So don't fall into the trap someday down the line when you're going to have two different bases, you're going to try to add them together. That's not going to be right. So since they are the same, we can say that log base 12 is the same as 9 times 16. Or, I'm sorry, it would be log base 12 of 9 times 16. And again, that's one of our properties. So then we multiply them together, and it turns out 144 is also equal to 12 squared. And so now we have 12 and 12. So that would simplify. Or we have a power right there. So we can move that in front. And now we have 12 of 12, which is 1. So we get 2. So you could also have, I mean, I guess technically you could have plugged this into your calculator, but not all calculators can you do an odd base like that. or a strange log base of that. Okay, so let's try another one. So log base 6 of 90 minus log base 6 of 9. So that is the same as saying log base 6 of 90 divided by 9. Then you can simplify it to that. And in this case, in order to solve it, again, not all calculators have that log base button that we discovered the other day. So you will have to change it to something that we know or that your calculator can handle. And that's either log base 10 or you can even use natural log in this situation. But it makes more sense to use log base 10 because we have a 10 there. So one of our properties, if we're changing the base, was, so if you're changing the base to something, you're going to take the, so we're changing it to log base 10. So then we're going to take our 10, log base 10 of 10 over our log base 10 of 6. And so this this equals our guy right down there. And then this is something you can plug into any scientific calculator. So I think a lot of you guys have like those with that super cool fancy graphing calculator that can do log base 6, but not all calculators can. This is something that a regular calculator can handle. And then you just plug it in and you get your answer. Too easy, right? Yes, that chart will probably be posted on the board so that you will have it available. So let's hear what we got. The justification for each step for simplifying log base 12 of 9 plus log base 12 of 16 and so on and so forth. Okay, let's see what our options are. So we've got this part right here. That's where we took two logs added together and they now were multiplied. So that is the product property of logarithms. Let me guess. It's not gonna, my program is glitching out. So that's what we'll go there. And then you could multiply them together. Multiply, that's your justification. You multiplied. You can simplify it to 12 squared. Pull the 2 out. This is the one we did earlier, isn't it? Yeah, it is. So this is just justifying each step. This part is not a thing that I would have on a test. I'm not going to have you guys be writing proofs. I'm going to be more interested in making sure that you guys know how to do this part of it. Because this is the part that you will see over and over again in different classes, different scientific concepts, and things like that. What single property of logarithms could you apply in order to verify these steps using only a calculator? I would assume change the base. That's what they're probably going for because your normal calculator can't do log base 12, so you'd have to turn them into like log base 10 or log base E, whatever. Try a word problem. So use a logarithmic model to solve a real-world problem. So Liberia's population, 4.7 million in 2017, annual increase 2.5%. So the population of the country, Liberia, has been increasing at about the same rate over the past several years. If this rate continues, how long will it take for the population to increase by 50%? So remember our exponential growth model is right there. That's that guy right there. Where P is our population in millions, T is years, P naught is the starting population in this case in 2017. R is the average growth rate as a decimal. So, okay, we know a couple of things. We have 4.7 million annual increase, so we have our rate. So we can plug all of that stuff in. Well, they're going to do some algebra first. and that's fine. So before they plug stuff in, they want to get this t by itself. So again, they want to know how long it will take to get somewhere. So they want to plug something in for this p and then be able to have that t come up with an answer. So first things first, we see that we're going to need to get this thing by itself. So before we do that, we're going to need to get this thing by itself. So we're going to divide both sides by p naught. Let's zoom in. So that's where we get this part right there from. So then we can take the log of both sides. So technically, we're over here, log of this one, and then we're going to use log base 1 plus r. And then, oh no, hang on. And then we've got our log over here. So that would cancel this out, which is why we have that t left over. So we have the log base 1 plus r of p over p naught. So what did they do after that? Oh yeah, so as I was about to mention, or what I was thinking, so log base 1 plus r is not a thing that our calculators can handle, unless that r is 9. And it would be log base 10. Haha, this is kind of like a joke. So we need to change the base of this, and the way we do that is, again, so log base of our new base, we're going to say log base 10, or common log of our thing right here, which is p over p naught, over our common log of 1 plus r. So at that point, we can plug stuff in for all these numbers, and we can get a number. So a little bit of algebra. Good times. So how does log base 1 plus r equal t follow from p over p naught equals 1 plus rt? Rewrite the expression form of equation in the equivalent logarithmic form, right? Yeah. Sorry. We had already done all of this, and now it's like, why are we going backwards? Anyway, so what property justifies this step? That's when we change bases. That's the change of base property of logarithm. So now we plug everything in that we have. And this is something that we can just plug into our calculator, and we get this number. So in what year will the population of Liberia be 50% greater than it was in 2017? So it's going to be 2017 plus 16.4. So we'd probably just say plus 16. I think we'd round down. So that would be 2033. Did I math right? Yay, I did. So there you go.